Hi, I'm Scott Braswell with the Nanotech User Facility at the University of Washington, and today we're going to do a training video on ebeam lithography. Lithography in general is a way of transferring a pattern. We use two different kinds of lithography to transfer patterns of very small size: photolithography and ebeam lithography, or EBL for short. Photolithography uses light to expose a photosensitive resist, similar to exposing silver emulsion in the photographic process. Light shines through a photomask like a transparency, and the pattern of the mask is reduced and transferred to the resist. After a short bath in Developer, you can see the pattern in the resist layer. With this method, we can generate patterns many millimeters down to single pattern elements of about 2 micron. The pattern transferred by photolithography will have the same thickness as the resist layer had. That's useful because we can backfill the lines and holes in the pattern with metals or oxides or nitrides to grow a pattern with the chemical and physical properties that we want. Alternately, we can etch the pattern into the silicon wafer itself and create deep troughs and holes where the resist was exposed. In order to create pattern elements with nanoscale dimensions, we need the resolution of an electron beam. In ebeam lithography, we use the electron beam of an SEM to copy our pattern onto a wafer coated with resist. It's a serial process, like tracing a picture out of a book, and so it takes much longer than a parallel process like photolithography. The first step in EBL training is to learn the software. Generate a design CAD file for the pattern that you want, and then a run file for the exposure conditions that you want. So that can be done on your own computer once you've installed the software. The second step is to come in and prepare the substrate. Once the substrate is ready, you can book some SEM time, come in and actually do the writing on the machine. The first step of the EBL process is preparing the substrate. So I start with a clean silicon wafer, and I'm going to rinse it first with acetone to remove any impurities, then isopropanol, and finally a distilled deionized water rinse, and then we'll dry it. So the first step is the acetone rinse. Before the acetone dries, you rinse it with isopropanol. To make sure there's no acetone residue. And then with distilled deionized water. And before the water dries, I use dry nitrogen to blow all the water droplets off of the surface. Both the back and the front. Once this wafer is clean, I can spin coat it with the ebeam sensitive resist and make sure that the bonding to the surface is good. The thickness of the resist layer on the wafer can be controlled by playing with the viscosity of the resist that we're applying and also the speed that it's spinning at. So to apply the resist layer, I'm going to use this spin coating machine here that has a vacuum chuck on top. I just set the clean wafer in the center, and then I'll test to see that the vacuum is holding by starting the machine. If the wafer starts to spin, then the vacuum is good. So I'm going to interrupt that process, and now I'm going to apply the resist. In this case, we're using a 3% polymethyl methacrylate resist. The resulting layer, after spinning this at 4,000 RPM, should be about 300 nanometers. I'm going to apply an excess of the resist And the extra volume will all spin off into the bowl. Each pipette full is about 1 milliliter. So for an entire wafer, I'm going to use 4 milliliters. As the thickness of the coating changes, you'll see the color of the wafer also changes. Until we reach our final thickness. And the resulting wafer, 300 nanometers thick, should be green color. Full spin time is 45 seconds. Now I'm going to transfer that wafer to a hot plate at 180 degrees for 1 minute. That'll drive off the excess solvent and solidify the resist. After 1 minute, I'm going to pull the wafer from the hot plate. Let it cool. And then before we pattern the surface, we'll break this into smaller pieces. The chamber size on our system is limited to about 5 centimeters in the X and the Y direction. So we can't write on this entire wafer. So the next thing I'm going to do is break it into smaller pieces so that it fits into our system. This wafer is single crystal silicon, and it'll break. It's so pure it'll break along a perfect cleavage line in the crystal plane. If I can just get a fracture started, it'll propagate all the way through. And so I can cut a perfectly square piece from this. The ideal size for our chamber is about 1 centimeter squared. The surface of this resist is featureless, so in order to have something to focus on so that I know that the resist is at the right height, I'm going to carve numbers into the corners on this chip. They don't need to be deep enough that they score the silicon, they just need to be through the resist layer. So I'm numbering the corners clockwise, 1 through 4. That'll give me a reference point when the chip is in the system. In addition to loading the chip, I need 2 standard samples. First, I'll load gold nanoparticle substrate because it has very good contrast and we can use it to optimize the beam before writing. It's kind of like sharpening your pencil before you draw a picture. And the second sample that we need is called the Faraday cup, and it's basically a 75 micron aperture that collects the entire beam so that we can measure the amount of current that's coming through. From that current, we can calculate the dosage that we need to expose the resist fully. And one last step before I load this into the chamber, I want to blow the debris from the surface of the chip that might have landed there from scribing the numbers into the corners. Now we'll load the sample into the chamber with standard procedures. The one difference is we flip the stage setting from A to C so that we can measure the current of the beam as it comes through. Our SEM is equipped with the Nabity NPGS nanometer pattern generation system. That includes the beam blanker and also a CPU equipped with a couple pieces of software. One of those software programs is DesignCAD, and that's the program we use to actually define the pattern that we're going to generate. The second piece of software is the actual NPGS run file software. That controls the exposure conditions that the microscope uses to generate that pattern with good fidelity. When we execute the run file, the NPGS computer is going to position the beam in the column using the scan coils on the SEM. This is the external beam blanker, which is also going to block the beam when it goes across parts of the pattern that are not exposed. Different EBL machines have a wide variety of performance. With this system, we routinely write lines of about 50 nanometers in width. Dedicated ebeam writers can also write fine lines of about 7 nanometers in width, and they have a lot of other advantages besides. After I've launched the NPGS menu, there's a link to the DesignCAD program. So I can open DesignCAD from this button. And DesignCAD has a lot of tools for making virtually any pattern you could want. Most of the useful tools you'll find under the NPGS tab. The one that I'll show you is most common one that we use is the dot array function. So if I pick dot array, it gives me a lot of instructions here on exactly what it wants to do, but I'm going to read hit the 0 to create the dots as filled circles, because I want an array of dots that aren't simply outlines but are whole patterns. So I type 0, the center of the array, OK, diameter of the dots, for example, we'll say 0.2 micron. That's 200 nanometer in diameter. Number of columns, we can say 100 for a round number. And the distance between columns, we'll say 0.4 micron, 400 nanometers. And then for rows, we'll use identical spacing. DesignCAD then generates an array, 100 columns by 100 rows, composed of 200 nanometer dots that'll be filled in by the e-beam, spaced 200 nanometers from one edge to the next. With that file made, I'm going to set the center of the array as the origin. So I select Max Mag. The pattern area is 40 micron by 40 micron, which shouldn't take too long by EBL. My estimate is the right time for this pattern would be about 10 minutes. The microscope magnification we need is about 5,500, and then I'll save that file and exit DesignCAD. The second piece of software in NPGS is the run file programs. I'm going to open Run File Editor through this button, and it generates a blank run file for me. There's one entity listed here, and that entity is a pattern. You see under pattern name it's blank. If I double click this field, it opens a menu. I can insert any pattern into this run file that I choose. For our demonstration today, there's a file called hex tries that I'd like to write. When I load hex tries into the run file, it then brings up a new list of options. And these are the different writing conditions that I can control on the SEM. This pattern is only one layer. The origin is 0, 0. The magnification that I found from CAD for the last pattern was 5,000. For the current pattern, because it's larger, the magnification needs to be 1,000. The frequency of exposures horizontally is the center-to-center distance. Those will be 20 nanometers apart. The line spacing is the frequency of exposures vertically. I'm going to set that to also be 20 nanometers. The configuration parameter is the same as the spot size on the SEM. And for the finest features, we want to use a spot size of 1 because it has the lowest current. And in the measured beam current field that comes next, it lists the units here as picoamps. And when I measured the picoamps earlier, I found that it was at about 13.9. The last option here, it says multiple pass mode, disable. This is standard for our system. The dwell color with the unit of microseconds is 261 microseconds. This is calculated from the measured beam current and the line dose that I want to expose my resist. In my experience, resist of this thickness and a pattern of this size will need a line dose of about 0.7 nanocoulombs per centimeter. So if I change the line dose here, you see that the software automatically updates the dwell color above. And then finally I save this run file. Now the run file is complete. We've loaded all of the microscope exposure conditions and we've loaded the pattern. So the computer has all the instructions it needs to reproduce this sample pattern hex tries by writing that pattern out on our chip. To prepare the microscope for ebeam lithography, we need to connect the ammeter to the port on the front of the SEM chamber door and connect the NPGS cable bundle from the CPU to the microscope control boards. This ammeter is connected to the BNC port on the SEM chamber, and it's going to measure the amount of current coming through the beam. I'm just going to change it to nanoamps. Once we measure how much current's coming from the beam, we can calculate the exposure time for the pattern that we're making. The purpose of loading the gold standard into the chamber is it provides really good contrast and high resolution. We always want to make sure the beam is in the best condition before we try writing a pattern by EBL. This is similar to sharpening your pencil before you draw a picture. So we first image the gold standard, focus at 100,000 magnification. We adjust the focus, the stigmation, and the lens alignment to make sure the scope is ready for writing. This is the Faraday cup. And to measure the beam current, I'm just going to zoom into the hole and read the current off of the ammeter. So it's reading nanoamps. It's actually about 13.9 picoamps. And I'll enter that into the run file so that it calculates the dose time. Because there's an ebeam sensitive resist on the surface of this chip, I don't want to look at it. Any of the areas that I view with the ebeam are going to be exposed. So I'm going to carefully approach it. I found the top edge. And I'm going to focus the beam in the corners. Each of the 4 corners will be focused at a slightly different height because the chip won't be perfectly flat. As I collect those 4 corners then, the NPGS program will calculate the plane of the chip so that it can focus no matter where on the chip we actually write the pattern. This is corner number 1. You can see I've scribed the number 1 through the resist layer here. I zoom in on it, you see that it's out of focus. I don't actually want to focus this in the normal way. What I want to do instead is raise the stage up until this comes into focus. So I'm going to need to turn the stage height on the chamber door over here on my right. And as I raise the stage up, the image on the screen comes into focus. By raising the stage up to the level that the beam is focused at, I keep all of the same beam conditions that I was just so careful to optimize on the gold standard. And now that this is in focus, I can record the working distance in the NPGS software. I'll repeat the same process at all 4 corners of this chip. And when it's finished, it will give me an error value to tell me how non-flat the chip is. In the NPGS program, I go to Commands and Direct Stage Control. And NPGS is going to prompt me to record the 4 different corners of the chip so that it can calculate the plane. I'm going to hit Enter to acquire new data. And I've already focused point number 1, so I'm going to hit space to acquire point number 1. And very briefly it read 6.39 millimeters, the distance from the lens where the electron beam exits to the surface of the resist sample. Now it prompts to acquire point number 2. At this point I'm going to go ahead and focus on the second corner of the chip, acquire that focal distance, and then I'll move to corner number 3, repeat the process. Now when I've collected all 4 corners, I push Enter. It calculates the chi-squared value for my chip. Then I push Enter to use those results and exit from the direct stage control. Now to confirm that the NPGS computer is in control of the microscope, I go to the Commands column, Set Blanker, Beam On, and turn on my external beam blanker. I confirm that the image shows up on the other screen. I can shut that off by setting blanker, beam off. So the beam blanker is now in the control of the NPGS computer. I'll also test that it's reading the working distance correctly. I click read working distance. It gives me a value of 6.38, which agrees with the 6.4 I'm reading from the SEM computer. Now on the SEM computer, change scan to external XY. Click Command, Digital Imaging, New File, Acquire. So this shows that the NPGS computer is getting the feedback from the microscope detector. Then I will confirm that the digital analog converter is calibrated. Under Command, Calibrate DACs, and this takes 40 seconds. After the DAC calibration, our system needs a small adjustment of 3.6 and 5, and then I can process the run file. After we've finished processing the run file, you can remove the chip from the chamber and take it over to the wet chemistry room for developing. The resist that we're using for our demonstration today is polymethyl methacrylate. It's a positive resist, which means the areas that are exposed to the e-beam, the bonds will break. And then after the exposure, we'll immerse it in a developer that's methyl isobutyl ketone in isopropanol. That developer will take the broken PMMA and rinse it out. So the exposed areas actually make troughs in the resist. Then we can post-bake for a harder product, more resilient pattern. After developing, you can see that we've managed to transfer our pattern into the surface of the resist. The areas of the pattern that were exposed to the e-beam are the deep portions of the pattern, and the unexposed resist is the higher surface. The total area that we've patterned is about 50 micron by 50 micron, and the right time on that today was about 30 seconds.